Reversing a single linked list. How can we reverse a linked list? Before starting this video, you should know what is a linked list and how we traverse through it. This is not for beginners. This is for those people who are already in touch with linked list and the concepts regarding to it. So let's see how can we actually reverse a linked list. Before writing a code, we shall see the approach. This is a linked list. It contains a data part and a link part. Now what I'm going to do. There are two approaches for solving this problem. One, using stack. Other one, by using iterative approach. Using stack is nothing but recursive approach. We can solve recursively, and other one is without a recursive approach, that is iterative approach. Any problem can be solved only in these ways. One is recursive and iterative. Let's see what I'm going to do. If this is a linked list, single linked list, I'm going to push initially null and current node. Suppose it's something like current node, and we don't have the predecessor to it. That predecessor is null. Initially we push the predecessor null and the current node onto the stack, and also code along with it to reverse the links. We shall observe what we are doing. Like, let's take the address of this as 0, 1, 2, 3. Right? I'm pushing the null and node 0 onto the top of the stack. After this, 1 and 2 onto the top of the stack. 3 and 4 on the top of the stack. As I said before, along with this, I'm going to push a code to change the links, right? What's happening after it? I pushed initially null and 0 along with the code to change the direction of links, and 1 and 2 and code to change the direction of links, and 3 and 4 change the direction of links. What happens now? Node 3 and node 4 are pushed onto the top of the stack. What we do is current node is equal to predecessor node, right? And the current node link is equal to predecessor. And here the code current node link equal to predecessor, current node link equal to predecessor, current node link equal to predecessor. This is how we are going to change the links of it. I hope it would be much clearer for you after I write the code. What I am doing here, you see this? These are the links. This is a linked list. What I am doing here is, okay, this is the first node. What I am passing to the reverse function, the null as a predecessor node to the first node, and the address of the first node. Let's suppose take the addresses as 0, 1, 2, 3. I'm pushing null and the 0. I'm passing the null and 0 to the function reverse. So reverse is from operating system calls main, and from main I'm calling reverse by giving the by passing null and address of the first node 0. What's happening here? And in predecessor node the value is going to be null, in current node address is equal to 0. And after this we are checking if current means current not equal to null, means the current node is still there. The current node has the address of the first node, right? When it is still there, what we are going to do, reverse of current, that is 0 comma current link 1, and along with this we have a code for changing the current node address to the, that is current node link to the predecessor, the previous node. We shall execute it later. First the preference is given to this method, then after predecessor is 0, current is 1, and reverse of 1, 2, and a note to change the links, predecessor 1, current 2. Let's take 0, 1, 2. Okay, only 2 is enough for explanation. Next 2, and also a code to change the address. What we are doing this, we executed it. The predecessor node is now 1, current node is equal to 2. What is the code here? Current link equal to predecessor is nothing but 2 link. The 2's link is going to be the predecessor, and when we come to the previous part, again we have one code left, that is current and predecessor. Now here predecessor is 0, next current is 1, current link equal to predecessor is equal to predecessor. And after coming to this area, now predecessor is equal to null, current is equal to 0. So current link equal to null. You got this point? Initially we had the links like this, so we change the links from the last node to its predecessor, the last node previous node to its predecessor, and from here to this node, and this node to null. So we don't have anything, we put it here as null. I said you before, I'm pushing the null and current node, and current node's next node as current node. This one is current and current next. Again, when we get the current node, we are pushing the current node and its current node next. Current node next. In the same way, current node and current node next is something like null. I'm pushing 0 onto it, and current node is 0, and it becomes predecessor. Initially something like it is a predecessor, and this is a current node. When the current node is 0 and it is not null, means address is 0th node, we are pushing current and current next is something like 0 and current next. When it is current next 1, it's going to be current and it's a predecessor. And again something like 2, when it is 2, its predecessor is current. It's nothing but current node next node is nothing but link predecessor, and current node, for this current node next node equal to predecessor, current node next node is equal to predecessor. This is the way you can actually approach this problem recursively. and we got some iterative solution for it. Here we need to understand this what we're doing it. You might find it a little bit confusing, but it's worth understanding what we're doing here. We are traversing until the end of the list without actually pushing it onto the stack. We're moving from one node to other node, one node to other node. We're changing the link one node to its previous node, one node to its previous node, and it to null. So how we are doing it? Let's write the code and trace how it actually is done. Pointer p equal to first. Why am I writing as first? I'm taking this is the first node. Assigning its address to it may be 0, like p equal to first is nothing but assigning the address of the first node to p. So see here, p equal to first. Next, q equal to null. Next, r. And I think in recursive we forgot to see the other point actually. Current link equal to predecessor, right? Okay, if there is a current link, we point it to the predecessor. And again, there's other point to it. Else, if there is no current link, like last, we are moving to the stage where this is going to become a current, and current next is going to be a null. In the situation when null becomes current, then what we have to do, during this situation, current should be equal to predecessor, because when current next is null, so we have to think about the predecessor node, right? Something like first equal to the predecessor. Something like when we have reversed the links, if this is a node, actually we have reversed the links, and the last node should become the first, right? So while we actually pushing the nodes onto the stack, and when the current becomes null, during that time we actually make this thing first is equal to predecessor. This is a predecessor and current, so first equal to predecessor. So when we actually change the links, the last node will become the first node. So write it here, else first equal to predecessor, and close this thing completely here. Now we are going to see the iterative solution, right? Okay, first null r. How we are doing this thing, you must be wondering, right? Yeah, how am I actually being able to write this iterative solution? right? How am I doing this? Look at the code much carefully. So this is the first node, and I'm assigning the same link to P. So P and first are pointing to the same node 0, 1, 2, 3. Let's take the address of this thing, like 0, 1, 2, 3. So what we are doing it, and we are putting this Q as null and R as nothing. Should trace through the code what it is saying. R equal to Q, nothing but R equal to Q. Q is null. R equal to Q. Q is P, the current node. So this is Q, and P equal to P link. So P is equal to this thing. Next, Q link is equal to R is nothing but Q link is null. Next, what we're doing, the same process. Again, R equal to Q. So R is 0. Next, Q equal to 1, P. P equal to P link. It's 2. So this is Q, this is P, and this is R. What we're doing here again, Q link is equal to R, 1 link is equal to 0. We are making this thing to point to here, and again the same process. R is 1, Q is P, P equal to P link, Q link is equal to R, right? This is R, this is Q, and this is P. What we are doing here, R equal to Q, Q equal to P, P equal to P link. Next, Q link equal to R, 2 link is equal to 1, and again, and we are going to change the links like this. This is how this code works. We are going to, it's pretty easy, like we are actually moving through the code. And we are making the 2 pointers, R, Q, P. Q pointer is equal to previous, and R is equal to and we made it initially null, and Q pointer is equal to previous, and P pointer is equal to the previous. This is how we are changing the links. This is how the iterative fashion we solve this, and it requires some practice to go through this. And I'll give a quick summary of this. What I'm doing in a recursive method, I'm pushing the null and the first node, and first node is current node and its next node, along with the link to return it. Here also along with the link, along with the code to return it, along with the current node's next node and a code to return it, and with the current node's next node along with the code to reverse it. Yeah, code to reverse it. So it is null. We are going to reverse it to previous, from here to here, from here to here, and from here to null. This null means it points to this, so I'm putting it here as null. This is how it works. And in iterative fashion, if the nodes are like this, R, Q, P, we are making it as null, and we are making it point to R and P to point to its previous node. This is how we are changing it in an iterative fashion. Hope this is clear for you.